Again, we heard a lot about OpenStack, Open Compute, and companies innovating in open standards yesterday. And if there's another company that is pioneering in this field, it's definitely Joyent. And with Jason Hoffman, we have a speaker where every time I listen to him, it's always an interesting talk. It's always an interesting twist there. So I'm sure he's not going to let us down on that again today. So with that, let me hand this over to Jason.
Thanks. Yeah, well, wow, lively morning crowd. Good. Yay, San Jose. What? Yeah. So I'm Jason Hoffman. I'm the founder of a company called Joyent, and have been the CTO of the company as well. We're an 8-year-old company, sometimes noted for basically having forked off of Solaris, Nevada Build 33, and going on our own since then. We at least have a couple lines of business. One of them is that we do actually run a lot of systems across about 8 data centers in the U.S., pretty large infrastructure as a service type offering. And then we actually ship software as well. And as you can imagine, sit around and do a lot of kernel engineering in-house and so on like that. My background's actually not in computer science. I actually was a chemist by training, that did a lot of sort of small molecule protein docking work, and then I ended up actually going to medical school, and then I did a doctorate in pathology, and I was doing large scale image analysis around those types of things. And so I've always been pretty much on the buy side of the house, if you will, and really started doing this company about 8 years ago or so to effectively build a new type of supercomputer. So how do we go from a traditional coupled synchronous shared memory supercomputer to a highly decoupled asynchronous non-shared memory supercomputer, and so on. So I thought I would actually give a very, very, very basic talk today. So meaning one, talking about just at least how I sort of think of the industry and what's going on in the industry, from a very sort of simple, IT perspective, and then sort of wrap it up at the end, talking a bit about data, not just storage, but what we actually are doing with data. And so I basically often say that this is sort of what we're heading into. We're heading into a world now where basically the world's the new computer. Not the network, not the this, not the that. We're basically ending up in a spot where we are shipping more CPUs per year than we have humans on the planet. We sit around and we have 10, 15 billion sort of devices sitting around on the internet. And so we really sit down and say that we have billions of devices out there with the network sort of functioning as a backplane, and some of these devices happen to be the size of a data center, some are the size of a phone, some are the size of a plane or a car or the like. But what we're really sort of sitting is we're moving into this basic space where we're going to start doing everything from an IT perspective really as a large machine-to-machine system, right? And so as we start thinking around that, what does a very large globally distributed machine-to-machine platform look like, and how much data would this type of thing generate, and what would we do with that data? And I find, at least from some general trends in the application space, really is, most of them are treating their transport protocols HTTP. We're really seeing application design where it's not a client-server type app anymore. It's actually more what I would call these real-time data synced peers, where you typically have a server on a device and you have a server in a data center, and they're actually passing messages between one another. And so in this type of world then, we've basically implicitly decided to go ahead and do a large distributed concurrent system by message passing, right? As a result of that, we often see a lot of things where technology stacks are actually becoming limited by the number of connections or open file descriptors you can use and the like. And then, as I'll point out some other things here too, my concept, at least around the data trend, if you will, if it is not the fact that data's big. We actually have genomes now, and we had genomes 20 years ago. And so there's always been a lot of potential data out there. What we're doing now is we're actually doing a lot of more what you'd call machine-generated data, and we're actually much more interested in looking at data in real time, and so on. So we have these sort of general things. Computers, of course, for me are simple. They're supposed to be mankind problem solvers. We access them via apps. Apps do things to data, and it's really just that simple. And so computers and what we do with them and what we do with our data is actually supposed to make our life better. And I have to sort of convince myself of this on a regular basis every time we're sitting there with computers that aren't working. And what we all technically want, of course, is we just want computers to work, scale, and be completely transparent when they don't work. And business-wise, I always want things to just be better, faster, cheaper. I'd actually like all three to be the case when possible. And so what I want to just sort of point out is from a basic economics point of view, what we do in this industry is nothing special compared to other industries. And then we're going to talk about big data. And in fact, what I generally find is that even if I'm sitting around and trying to figure out where to put my data, how do I need to access it, how's that data still going to be around 20, 30, 40, 50 years from now, since we've never actually done that well either. One of the big problems that I sort of keep in mind is that we have a very difficult time sort of relating IT spend and infrastructure spend on the actual business value that's generated by it. I also sort of sit down and say when I look at trends within time, we sort of see this type of centralized to decentralized to distributed type systems popping up, and so I sort of generically talk about 1995-ish as being the point in time where most of us started saying, oh, geez, there's a internet going on. 2005-ish, about a decade later, we said, oh, geez, there's more compute going on too. Let's call that cloud computing or the intercompute, if you will. And I think a lot of us now in sort of the storage and data space are looking and saying, well, chances are there's probably another thing popping up in about 2015 where we're going to start looking and thinking about doing some interesting things around data, not just storing it. And also dealing with the fact, as I'm sort of going to show you, is that we actually are going and making storage every year at quantities that are pretty good sized, yet only about 1% of that shows up in what you'd call the enterprise storage market. The other 99% is ending up on device. And so again, if we sort of look at ourselves where in 2015, 2020, we're actually sitting now and saying that I actually have zettabytes and zettabytes of storage distributed across tens of billions of devices throughout the world, and only 1% of that's ending up inside a data center. What really are sort of data and storage type semantics in that type of environment? And I think as we're sort of sitting around, and we'll talk about this just a little bit at the end, as we're sort of sitting around and saying, well, what do I want from that type of platform, 10 years from now? How do I want to sort of address those types of things? And what are some basic semantics that have to be introduced into storage to accomplish that? Now, of course, economics are very simple, and this is why I was saying that what we do with computers is a normal economic system like everything else. In economics, you have a good, you have services, and of course you have a service delivery time. And so, for example, if I'm actually a farmer doing soybeans, I have soybeans and I measure it in mass. I have the movement of soybeans that I do mass per time, and I have time being how long it took to do that. And so that's a basic three fundamental things we sort of always do. And so this typically happens via sort of a service route as well. We have these transport hubs and ports within our normal systems. We send it last mile to the destination, and so on like that. We even see things where we start looking around a picture like this, which is traditional shipping routes in Asia in the 17th and 18th century. And we sort of sit there and say, it turns out that we actually laid fiber all along the same shipping routes. And so as we start thinking around our industry does have these basic sort of economic good services and service delivery times that we actually do a pretty bad job of exposing just these fundamental things, right? I have bits that I measure in bytes. I have bandwidth that I do bits per time. I have latency. And so to give you an example of this, people often talk about things like latency as if it's a network-only event. Yet, of course, for all of us that are doing things where we're actually touching disk, latency is, of course, a big thing there. And in fact, when you sort of sit there and you say, well, I'm going to go and use something like an I/O stat to see how my stuff is busy, well, that just tells you what the device is doing. When the truth is you actually sit there and you have 7, 8, 9 other layers of software on top of that, and most importantly, you don't just have the stuff, you have the transition between the stuffs, the interfaces. I mean, I used to point this out all the time in sort of the chemistry world, that there are people that study water, and there are people that study air, and there are people that study the interface between those two, and that's a valid field, right? And so we sort of sit there and say, there are, in fact, a lot of latencies within the system. And I think one thing we've been trying to do, at least on my team, is how do we actually sit down and have end-to-end latency measurements within servers? Where I don't want to do things like percent CPU usage, I want to do code execution latency. I don't want to go through and measure how many random IOPS are occurring on storage. I actually want to sit down and understand the latency of every type of event at every type of layer, and how do I do those types of things like that. And so bit, bandwidth, latencies, we have network bandwidth, memory bandwidth, disk bandwidth, right? And so when we sort of sit down and say that those are the different ones, we have, of course, the same thing in our industry as well. We have service routes, we have transport hubs, and we send last mile to destination. And when we sort of think around this from an sort of analogies perspective, is remember the internet, when we did the internet, and if we're going to do the intercompute, and if the future is the interdata, meaning cloud networking, cloud computing, cloud data, distributed networking, distributed computing, distributed data, remember that it was still infrastructure companies that came in and laid down fiber, right? So Level 3, for example, was a division of Peter Kiewit & Sons, a 150-year-old construction company. Mining, railroad, shipping companies actually sort of laid fiber. And then we see fiber owners now sitting down and starting to lay data centers and to put a lot more compute and storage inside of them. And then, of course, it also means that fundamentally a data center is a port. Data center is a factory. The ownership rules apply to it. If you can use your factory all the time, own a factory. If you can't use your factory all the time, don't own a factory. If you're sort of sitting down and saying, where do we actually need data centers and what should they be doing, they should be sitting at some sort of transport hub to do stuff. And so altogether, of course, the bits are economic good. The transport of bits is our economic service. Latency is our service delivery time. It occurs via fiber routes. It actually arrives at destinations. It arrives at ports we call data centers and goes out to final destinations we call devices. And we even have containers for these things, just like we have containers in the traditional sort of go out and ship things, right? And so we see things, of course, like the Evergreen, shipping company there out of Taiwan. It is a fact that things like the standardization of those containers on these ships was actually inspired by Paul Barron's, packet work. That, oh, geez, we should do something like that. We should have a very sort of standardized things. And in fact, when we look at the way that we're currently containing bits in our computers, on the network we call it a PDU, of course. In the case of Ethernet, PDU that we do as a packet. The thing that we actually contain bits within memory is a memory word, right? That's where the 8-bit, 16-bit, 32-bit, 64-bit comes from. We do things inside registers, and then on disk we put things in a block of a certain size. And so we have container concepts within what we do as well. And so we have this same sort of centralized, decentralized, distributed type concept that comes up. And the sort of process of going from centralized to decentralized and distributed is a very normal process in any industry. And it's a key thing to realize that distributed is actually a superset of it. It's not something that's mutually exclusive. And so most of what we're talking about is readily available economic goods. Those are commodities. Readily available economic services. Those are utilities. And so the bit business is a commodity business, and the bandwidth business is a utility business. And typically what we're doing when someone comes along and says cloud, what we're usually doing is something like a commodity or a utility market for either network compute or data. It would actually more appropriately call that storage, not just data. Because we end up, and this is sort of what we'll hit at the end, we end up with the concept that ultimately the thing that's not a commodity to us is our data, right? And so on. And in fact, I usually sit down and I say that the way to understand the trends in the industry is at least really around the idea that we're basically like a 3-cylinder diesel engine, right? And so, if you, of course, know how a diesel engine works, there's not a spark, it comes from pressure. And so we basically sit down, put in pressure, investment, fuel, compress, blow up, and we're almost constantly sort of sitting down and saying, let's do some interesting networking things, which then makes sort of interesting compute things, which then makes interesting data things, which then makes us do interesting compute things, and we sort of see ourselves almost constantly cycling between these 3 cylinders. And I think this type of thing where, cloud computing was hot, I don't know, the last couple of years, and now big data is going to be hot, and then yet people sit around and say, well, yes, but in order for that to work, we got to do this with the network, and we're almost sort of constantly just cycling between these 3 things in our industry. Just to give you some numbers to keep in mind, this, for example, is international bandwidth numbers. They're actually not that large, oddly enough. We only do about a couple terabits per second right now between us and, say, the UK. If we look at pictures are relatively small. If we look at things like this, in 2014, the projected global international bandwidth use is about 50 terabits per second, which doesn't sound that impressive because you can do that with a couple of routers. We can do a terabit per second of connectivity rack nowadays, right? And so, sending things, across cables isn't that much. I think it's also, even when people sit around and talk about public versus private cloud and public versus private data stores and so on like that, it'll probably land a lot like how the internet landed, if you will. It ended up being about 75, 80% public and about 25, 20% private in terms of what people do from a connectivity. We'll probably end up and keep that trend, right? If that was a trend in the network part, it'll probably be the trend in the compute part, it'll probably be the trend in the data part. If we look at what we're doing from a compute point of view, Intel, for example, shipped 15 billion processor cores last year, and we're still shipping on the order of about 10 billion embedded 8 and 16-bit processors as well out there in the world, right? And so, we're still literally shipping 8-bit and 16-bit systems, globally. And if we look at data, of course, as I was saying, is the point of all of it. It's what we're fundamentally storing at the end of the day. We have a couple sort of factors for all data stores that you're doing. It always comes down to volatility, access time, and size, basically vectored with cost, right? And so even when we sit down and say one of the beautiful things about a file system like a ZFS is that it's actually very conscious of what the future is going to look like, meaning that if I could actually sit down and have a board where I have normal sort of RAM slots and I have DRAM that I put in some and non-volatile RAM that I put in others, great. Well, that's fine. If that, from a cost perspective, works out just great, then it means that, the motherboard of the future just sort of sits down and has non-volatile RAM and volatile RAM on it. And the only reason we would have those 2 different things is because there'd be a difference in terms of access time, volatility, and cost, right? And what I can fit inside of that. If I can actually now start putting a terabyte of DRAM on a box and 4 terabytes of non-volatile RAM on a box, and I can do that in a server that costs less than $40,000 or $20,000 to do, that's what the hardware, of course, is going to begin to sort of look like. And so one thing we do, my group as well, is we sort of tend to track these basic types of things across the component market and cost that's going on as we sit down and sort of say what a piece of hardware that we're using should look like. And of course, it's important to understand where data comes from. It doesn't come from a lot of places. It comes from the natural world, it comes from machine activities, and it comes from human activities. That's it. And these sort of have different implications as a result of this data. So in the natural world, if I'm going out and collecting oil and gas data that's fundamentally in the ground, then a very common thing that I think of is, well, why would I pay to store something if I can go and get it again for cheaper within a reasonable period of time? And so you actually have things like, oh, all of my storage just filled up with my oil and gas stuff, so now it's time to just start deleting it. And if we need it again, we'll go back and get it. If I've been actually sequencing genomes out of a population of bacteria, it's actually cheaper to go back and resequence it 5 years later than it is to store that data for 5 years, right? And so we start really sort of thinking around the natural world as being a source of data, but it also happens to be the most dense repository of data as well. If NASA can actually come up with a telescope that can actually generate an exabyte of data per day, where's that data coming from? It's coming from observing the natural world at a certain resolution. And then we sort of sit down and we say, I'd say the last 10, 15 years, we've actually been pretty obsessed with human activities, humans generating data, user-generated data, me doing pictures, someone blogging, someone putting something on Facebook and the like. And in fact, a company like Google is entirely concerned with going out, collecting, crawling, aggregating, and making search available really predominantly around human-generated data. And I think what we're especially starting to see now is as we're sort of heading into the billions of devices world, where all those devices are also generating data, that we're actually going to be sitting down, and 2015 becomes also a sort of year that's mentioned pretty often because it's also the year where machine-generated data is expected to exponentially go past user-generated data and just continue from there. And so it becomes like this, sort of natural world-ish observation where now what we're actually doing is we're collecting a tremendous amount of data from things that we've made. And that's going to be an interesting time. If we look at things like the entire the entire storage market, IDC, for example, said that last year we actually made about 1,500 exabytes of what you would call storage. So flash storage that ends up in a phone or a projector or a laptop or the like. But when someone sort of sat down and said this thing will either permanently or not permanently store something on it, that's about 1,500 exabytes, 1.5 billion petabytes we did. Only 15 exabytes of that showed up in what you'd call the enterprise storage market. And so again, the interesting thing here is we have the explosion of devices and storage on devices. We're actually hitting a point now where you could sit down with iPhones and iPads alone, and you could do the math, and the storage on all the iPhones and iPads of the world basically adds up to the entire enterprise storage market. So is it possible to do something like take a complete backup of every iPhone and iPad once a year? Yes, it would be, except it would mean that Apple would buy all the storage in existence, right? So none of us would do things like that. I had a similar sort of thing where, about a decade or so, I was running a data mining group that was pretty obsessed with going out and identifying failed drug candidates that had an interesting side effect. And that was actually being driven mainly by the fact that all of a sudden Pfizer had a $6 billion a year drug called Viagra that was a side effect of a thing. And so, of course, there was this whole thing where, as you can imagine, being yelled at by basically a Swiss pharmaceutical VP about how we're losing $500, $600 million a month because we basically also do not have an erectile dysfunction drug. And so what do? Well, we got to data mine everything that we have. We got to put it in a big data store. And I just remember doing things like calling up our NetApp rep and saying, I need 12 petabytes of storage. And his response was, well, we're only making 4 this year. And I said, well, it's going to be a big order then. And so, that for me, well over about a decade or so ago, was an education that, oh my God, there is a limited supply of these things relative to some problems that you want to go after. And so we can sort of sit down and say that there are, in fact, singular problems and data sources that would currently exhaust the world's supply of network compute and data if we just decided that we wanted to go and do it. So when we sit down and we say things like a good biotechnology example, rapid DNA sequencers are now cheap. It's literally 1/10,000th the price to do the sequencing as it was, say, 10 years ago. And 2008 in the genomics industry was a good crossover point because, see, you got to understand, in the Human Genome Project, what was decided was every sequencer in existence was going to do the Human Genome Project to get this genome done. It's literally a massive rounding up of all resources to accomplish this given task. That's why it was a big project. Now, all of a sudden, everyone and their mother can basically buy a DNA sequencer for $100,000, $200,000 for their lab, and the output of a single one of those is equivalent to the entire output of the entire Human Genome Project. And so what happened in 2008 was this funny sort of math where we said, well, if we turn all these on, we'll actually exhaust the world's supply of hard drives every 4 days. Right? And so, you have this funny sort of thing where if I wanted to sit down and sequence the genomes of 5% of the US population, I would exhaust the enterprise storage market. Right? And so you can't. And so there are, in fact, these pretty good problems. And this is, as I was saying earlier, is a great example of unique versus non-unique data and how there's a true difference between data that can be easily and cheaply regenerated in the future. And so you always sort of sit down and say, is it unique, is it not unique, is it cheaper to regenerate it, and so on like that. And that becomes a normal sort of decision process when you're actually at the limits of what you can even buy or source. And so we have fun things like if you actually look at now the idea that automobiles are shipping with 100 to 200 CPUs inside of it. Automobiles are completely instrumenting stuff. If you wanted to keep all raw instrumentation data, you can actually have things like single car manufacturers exhausting the world's supply of enterprise storage, just based on keeping all that sensor data. You have things where one Boeing 737 with 2 jets generates 480 terabytes of instrumentation data off of the 2 jet engines. And in the US alone, we do 30,000 flights like these a day. And so again, you sit down and you begin to do this idea where you say, well, okay, so I could collect all of this, and if I did that, then I'm saying, well, it's half a petabyte, and so, okay, so that's 10 exabytes of stuff that I'm doing, in a day, in the entire market, 15 exabytes, and so it takes 2 days if I wanted to do all of that. So guess what? We actually can't do it. And yet, all of these things are actually generating this data, and then what we're typically doing is just dev nulling it, right? And there's actually now a desire to not do that. And that's why we sort of sit down and say there is, in fact, going to be machine-generated data and sensor data that's going to exponentially go past what user-generated data is. How's that going to be stored? How's that going to be indexed? Will there be a new type of Google as a company that sort of emerges to do something like that? And so we sort of sit down, and we have this machine-generated data, observation-generated data, both basically surpassing what the user-generated sort of data is. And we can sit around and within that world realistically say that storage needs to be 1 million or 1 billion times better to go and do some things we would like to do as humans. And so, we have to go do that. And we have sort of a general complaint as well, is that currently what we're doing, at the level of what you would call storage is very simple 1985, let's do NFS stuff, right? When in fact what we're really not doing is we're not sitting around and saying, well, maybe I actually want a little bit better hooks within the storage itself around being able to sit down and say, is data unique or not unique? Can I actually sit down and say, if unique, what's the value of my efforts or my business in regards to this data? And can you actually sit down and do intelligent policies around that just based on what I just told you? If I told you things like no one can ever see this, then you automatically encrypt it. If I tell you that you can never lose this, then you never, ever, ever put it on a non-rated system in only one data center. You sit down and you start saying, maybe we can actually introduce some very sort of basic data-centric concepts inside storage today where we just sort of sit there and say, this is my data, it's unique, don't lose it. And the system goes and does it. And it even understands that at a given scale that you might need, it understands things like, well, bit rot and everything else like that, and what would sort of be doing. And so I think sitting down and saying, How do we sort of really make these types of semantics clear at the storage layer? How do we sort of sit down, even right now, I think Bill yesterday was talking about some I/O throttling stuff we've done. How do we explicitly trade off predictability with high performance? And then how do I just know things like my data is going to be there in 25 years? I mean, you have just one simple example there is you look very often, you'll say in things like the movie post-production type teams, right? Where they sit down and very often they go through. I was talking to the guy who did all the post-production on the Lord of the Rings movies, and he says when production was called, they went and they grabbed everyone's computers and they encased them in carbonite and plexiglass, basically, right? Because 20, 25 years later, when the full rights of the movie come back, then they can sit down like George Lucas did and basically bastardize those films too, right? And on that note, thank you. That's it. Is there like a Q&A, something?
Yeah, sure.
No, or
There's always some question out there for you.
get off the stage.
Not that fast. Questions for Jason?
Sorry, it's a very it was a fluffy light talk, so it's not like there was any hard technical stuff in it. But I swear they told me it was sort of Keynote-ish. But no?
Well,
Yeah.
there's one. Finally, someone from the backbench. Appreciate it.
I was just wondering about your comment about human genetic sequence data,
Yeah.
and whether that was the raw data or whether it had been compressed in the usual ways.
That's like raw image data. It's also a good example of if you actually go into the pure text output. One, it's naturally compressed, right? Because it's just strings of text with no white space. The thing, though, that's really interesting is in a large-scale project like that, we still haven't actually sat down and done this, basically the signaling and image work well. So you sit down across, a very large genome, and you say, like, well, can I really sit down and tell you, with a great certainty that you have this defect when, in fact, we actually can't read, the colors well yet. And so a lot of the times when you have a unique thing that you've gone and sequenced, you keep all the raw image data and everything else, because even in that, the current systems are not good enough to translate it through.
Thanks.
Okay. Yeah. Thank you.